Yep, and then we talked about the Mulliken population analysis. This is all going to be useful to really talk about the bonding. So right now we haven't talked about bonds at all. So the next question we're going to ask are, where are the bonds? Just going to check to see where I am in the frame of things. Okay, cool. Okay, so if we think back to the Mulliken population analysis, two-centered orbital. We had one which was equal to psi squared d tau, and then we expanded this out using linear combination of atomic orbitals. Star to like that, d tau. We eventually arrived at the following expression. Right? You remember that? I selfishly made you guys derive that. Where in here is there bonding information? Or information about the interaction between basis function 1 and 2? So, not, that would be here in the final part. Mm-hmm. Yeah, this bit here. That tells you about the interaction between the two particles. This tells you like control of electrons on atom center number 1, number 2, and then the electron shared between them, right? So the 2C1, C2, S12 term can tell us about the bond between I1, I2. If C1 and C2 the same sign, I think this is what you were thinking about, Joe. If they have the same sign, what type of interaction is this? Constructive, yep. Which means what type of bonding? What type of interaction I meant? Bonding, yeah.
Is that always true?
Oh, where we were moving in phase and out of phase, you mean? Or?
Like the ones that had passed and there was like...
Oh, yes, and we had butadiene. In some cases, like you were talking about, you don't have to draw this.
No.
Like that?
Are you talking about like the band structure?
I'm talking about the one where there was like, there's 3 p orbitals and they were all in like the same direction. So
yes.
they were all shaded like the same way, but then it wasn't constructive overlap between them. It was deconstructive.
Yeah. So you're talking about.
Yeah.
Fuck. Like that?
Yeah. that like a
No, in this case, they would have differing signs because there's not overlap between them.
okay.
Okay?
So like the way we write them out for the like LCAO, and then this is
Different. Yes.
Okay.
The LCAO approximation is just like writing it out generally like this. And then we're talking about interaction between two atoms. Not more right now, just two of them. Okay. I thought you were talking about something like this, where is this bonding or anti-bonding? Well, it's anti-bonding along carbon number 1 and carbon number 2. Carbon 2 and 3, it's bonding. And then carbon 3 and 4, it's anti-bonding. So, but we're talking about two center interactions right now. We're picking specifically two atoms, or two atom centers. Okay, if they have the same sign, it's constructive. If different signs, yep. Destructive, anti-bonding. So that term I just erased, it basically tells us if we have a bonding interaction or an anti-bonding interaction, right? What about if we multiply that by the DOS? That can tell us populated versus unpopulated states, and that can give us an idea what interactions are bonding, what interactions are anti-bonding. So if we simply multiply this overlap term by the DOS, we get an idea of where the DOS is bonding and anti-bonding. Between atom pairs, so we have to select pairs of atoms. By doing this, we get a new property, a new parameter. This is called the crystal orbital overlap population. Or if you were going to shorten that, what would you shorten that to? Yep, COOP. The COOP. Okay, we showed for a 2-atom system, but for a many-atom system, you have something called an overlap matrix. Overlap matrix is multiplied by the DOS. So you multiply it by the DOS matrix. Enough of words, let's draw some pictures. Yeah.
Is it like a cross product or is it more of a dot?
You just are multiplying.
Oh, okay.
Yep. Okay. We're going to drop back to the simple system that we've been studying for a while. What simple system do you think we're going to go to? Yep, we're going to drop back to the H chain. Let's consider one D H chain, infinitely long. Yet again. We're going to plot the band structure. What are my limits for my y-axis, or x-axis? I'm sorry. Yep. Okay. Then we're going to plot the DOS. Then we're going to plot the COOP. Yes. For, I have many favorite methods for many different things. Are you talking?
Like, would you prefer COOP or
COHOP? COHOP is more valuable. We'll talk about why that is in a little bit, but you have to understand COOP to understand COHOP. Or at least it's easier that way. COOP can sort of tell you like a bond order, but not really. It fails in that regard. But it worked well at the time when computers weren't fast enough to do a lot of this other stuff. Co-ops give you an idea of how much this bonding and anti-bonding contribution contributes to the energy. So it gives you like a numerical value. And then there's another one called COBE, which is about bond indexes, which tells you about number of bonds. Anyways, let's plot this stuff out. Okay, I'm going to use yellow. Is that okay? Okay, band structure for this thing. How's it look? Low to high, high to low? Yeah. Density of states, demon horns. COOP. Now, notice I've indicated a positive end, negative end. Positive meaning what type of interaction? Bonding. Negative? Right. Okay, before we plot this, let's plot the block functions at different points. So, question. What do the block functions look like at k is equal to 0, pi over 2a, pi over a? Let's mark these points in red under band structure. We're talking about here, the other end, and where else? Yep, right in the center. We have k, 0, pi over 2a, pi over a. And then we're going to draw what the block function looks like. At 0, remember we're not changing phase. What should that look like? Yep. Now, what about for a? Or pi over a, excuse me. Yep. Positive, negative, positive, negative. Pi over 2a, we're in the center. What's going to happen there? So at 0, we get a bonding combination. At pi over a, we get anti-bonding in the dead center. Yeah, Non-bonding. No character on that s orbital. Switches phase, so on. So we get bonding, anti-bonding. What about the center? Okay. Now, let's try to plot out our COOP. And remember, it's the overlap integral, or overlap, multiplied by our density of states. So where's the most bonding interaction? Yeah, right at the beginning. So we're going to go like that. Where's the most anti-bonding? Very end, yep. And what about in the center? Where should I cross, or where should I be at? Should be at 0. What this plot is going to look like is that. So it's an easy graphical way to show which states are bonding, which ones are anti-bonding. By the way, where's the Fermi level for this system? Yeah. Yep. Okay. Any questions about this one? I think it does too. Tells you a lot of useful information too. Yeah. It is symmetrical in this case. It won't be, when you calculate stuff out, a lot of times this ends up going way bigger. And it can change. Okay, so next question. Can the COOP tell us about bond strength?
No.
No, not really. It's been shown to be really ineffective for d orbitals in other instances where it just doesn't work. But at the time, that's what they had to run off on. It worked out okay. It wasn't until 1993 where the COOP was formulated.
So we're dealing with a pretty neat
Yeah. Honestly, Joe, in most